So we having the directional derivative of the function, we can also say this is the rate of change of the function in direction of u. So that's also derivative of the function, maximum rate of change, directional derivative, maximum rate of change. So both things are same. I'm going to give you some more examples regarding the directional derivatives and the gradient, and also the results I've just discussed, the maximum rate of increase or minimum rate of decrease. So for example, we have here an example, we want to find the gradient of the function x squared plus y squared minus 4z, three-dimensional function of x, y, and z, and find the direction of the maximum increase of the function at the point 2, 1, and 1. So this is the problem. We first find here the solution of this one. We find the gradient of this one, and our gradient of the function at the point x, y, z, as I discussed before. Let's here f of x I plus f of y j plus f of z k, and the derivative with respect to x, taking y and z a constant, is equal to 2xi. The respect to y is plus 2yj, and plus z is minus 4k. So this is part 1. This is the gradient of the function. Now I want to find the direction of the maximum increase, direction of the maximum increase of the function at the point p 2, 1, 1 is the gradient of the function at the point 2, 1, and 1. If we have maximum decrease, then we have a minus. So here we write the gradient of the function, the direction of maximum increase is this direction. Taking the value x equal to 2, we get 4i, y equal to 1, get here 2j, and z equal to 1, get here minus 4k. So this is the direction of maximum increase. In this example, we are having given the temperature distribution in a space by the function 10 over x squared plus y squared plus z squared, is temperature distribution function. I want to find the rate of change of t with respect to the distance at point p. Point p is 1, 2, and minus 3. In direction of the vector a, that's I plus minus j plus k. The second part is in what direction from p does t increase most rapidly, and c is the maximum rate of change of t at p. So we go step by step. We take number first a, the rate of change with respect to the distance. Rate of change is same as I told, that's the directional derivative. That means we want to find the directional derivative of the function at the point in direction of vector a. So we want to find this solution of this one. Will be here, the steps will be, we find the gradient first, find the gradient of the function, then we find the gradient of the function at the point given is 1, 3, and minus 2, and after that we find the unit vector, and then we find the directional derivative of the function at the point 3, minus 2 in direction of vector u. This is gradient of the function at the point 1, 3, minus 2 into the product u. That's my, here is my a, that's my solution. So go step by step. Again, the function t x y z is given function is equal to 10 into x squared plus y squared plus z squared to power minus 1. So I take the partial derivative of this one with respect to x, partial t by partial x is equal to minus 10 into x squared plus y squared plus z squared to 1 minus 1 is 2, and then derivative inside with respect to x, that's equal to 2x. So if we simplify this one, I'll get here this equal to minus 20x over x squared plus y squared plus z squared whole square. So similar to this one, I can find the partial derivative of t with respect to y, this is equal to minus 20y, because we have the same, here we get here 2y with respect to y, with respect to z will be 2z over, I am having here x squared plus y squared plus z squared to power 2, that's my denominator in case of the taking the derivative. So I find partial t by partial z, so my partial t by partial z is equal to minus 20z over, I get here x squared plus y squared plus z squared whole square. Now I have the partial derivatives, I can write my gradient. My gradient of the function is equal to t is equal to partial t by partial x I plus partial t by partial y j plus partial t by partial z k. So here I can write my result. This is equal to minus 20x over x square plus y square plus z square whole square I minus, we have minus 20y over x square plus y square plus z square whole square j. Then we have plus minus 20z over, we have x square plus y square plus z square whole square k. Now I can simplify this one by taking something common. I have the gradient of the function t at any point x, y and z is equal to minus 20 we take out, and here also we take that x square plus y square plus z square whole square out. I get here xi plus yj plus zk. So this is my gradient at the point. We want to find the gradient of the function at the point x is 1. We take here the point here given to me is here is a 1, 3 and minus 2. So y is equal to 3 and minus 2. So I find the value of this x square plus y square plus z square is equal to 1 plus 9 plus 4 is equal to 14. I take square of this one, x square plus y square plus z square is equal to 196. Now I can write here the gradient of the function at the point 1, 3 and minus 2 that will give me minus 20 over 196, and here I get x equal to 1, we get here I, y equal to 3, we get here 3j, and z equal to minus 2, we get here minus 2. This is my gradient. Now I find my unit vector. My vector A given to me is equal to, here is my vector A is I minus j plus k. This is my vector A. This is I minus j plus k. To find the unit vector, I take magnitude of vector A. So magnitude of vector A is equal to 1 plus 1 plus 1 under the root, and this is equal to 3 under the root. So I can write my unit vector U is equal to A over magnitude of A. That give me 1 upon root of 3 I minus 1 upon root of 3 j plus 1 upon root of 3 k. So to find the directional derivative of the function t at the point 1, 3 minus 2, we have the gradient of the function at the point 1, 3 and minus 2, dot product of the u. We take this one, we take the dot product of this one, we get minus 20 over 196, we take it as out. Then we have here 1 upon root of 3, we can take that one out, that's no problem. We get it 3 over root of 3 minus 2 over root of 3. So we simplify this one. After simplification, we get here the result equal to 20. Here we get minus 3, and we simplify this one. We get here minus 20 over 196, and here is 5 and 1 is 4. We get here minus 4 over root of 3, and we multiply here, we get here 80 into 196 into root of 3. So this is the result of the directional derivative at the point. So this is my part 1 of the problem. We go to part 2.